Okay, let's move into the subject. And I make no apologies that we're going to look at the laws of thermodynamics. Wow, you say, I didn't know that I had to pass that. There will be a test, of course, at the end, and Alex can do all the marking. No, that's just for fun. We'll look at the crucial issue initially of the thermodynamics of closed and open systems. And you'll see why this is important as the talk develops. Then we'll move into the issue of information. The DVD actually is an older version of the talk and doesn't really deal with some of the huge implications that there are for the last point. That came later, and the second paper really develops that. So this talk hopefully will include that in a better presentation, in as much as I've thought things through a lot more since I did the first DVD. Now, the laws of thermodynamics, basically, it's a straightforward one, the first one, which is, it used to be that people said that matter can neither be created nor destroyed. Then post-Einstein and post the terrible things that emerged from the nuclear revelations, particularly in the Second World War, it then became energy can neither be created nor destroyed, because obviously there is a correspondence, we all know now, between matter and energy. For some quirky reason, it's all defined by energy going in, when really you'd have thought naturally it would be the energy going out. So in my little illustration there, I've had to be consistent because most people write it that way. And so if energy is going out, it becomes a minus. So don't worry too much about that. It's just a detail. And this law is a very important law because it basically says that there must always be the same total amount of energy that you had to begin with, whatever you're doing with it. The second law is often misunderstood, and I personally avoid writing it in terms of order and disorder, even though there is a link. I think it's better not to go down that line, certainly initially, unless you really do know something about gas dynamics and the way molecules behave. So it's far better, I think, to go to the original definition, which is all basically to do with heat and whether the heat or the energy coming off is of any use. If it's no use, then it's just dissipated energy. If it's actually of use, then it's called, I've used the term, useful energy. If it's dissipated energy, for various reasons, we define it as energy per degree, and we call that entropy. I'm not going to go into all the details of this, but it basically is, if you really want to use loosely a sort of a layman's definition, it's that there is no free lunch. You cannot get something for nothing. You're always going to lose that, some of that which you've got. You're never going to have a perfect machine. I'm going to actually bring a definition in a few slides, which actually brings things a little bit tighter. But for most people can just about follow that, even if you're not done a course in Thermodynamics 101, at least you're getting hopefully the basic idea. One of the most important points is, though, this is true for an isolated system where you basically got nothing coming in or out, that there is always going to be a rise in the useless energy per degree. Now, of course, people try to get around that by saying when it comes to things like abiogenesis and strong evolutionary proposals, this was put to me once by none other than the colleague from Oxford, Professor Richard Dawkins, on a famous interchange I had once. He said, oh, there's loads of energy out there to build the machinery of life. We were basically trying to address the issue of abiogenesis. Now, he made this very strong claim that as long as we recognize that we don't have an isolated system, we actually have an open system. And of course, that's quite correct. the Earth and all that's in it is quite open to energy coming in, obviously, from the sun and coming in also from space. And so the idea is that energy coming in could actually build the machinery of life, and that there is no thermodynamic problem. They are absolutely right that you cannot actually appeal directly to a second law because that is to do with an isolated system. But is that true scientifically is what I've been addressing in both those papers. Let me bring you to something very obvious, but I think it helps to have illustrations. As we heard in the plenary, he constantly was illustrating. I'm trying to illustrate so that you get an idea. Look at the beautiful leaves. We see them all around us in this beautiful area of Viswa. And the energy coming in is doing something in that leaf. Now, why is it doing it? What is happening thermodynamically? Is something happening differently to a leaf which is alive on a tree to what is happening here, where we've got some dead leaves, where energy is coming in? Is it different? Well, I assure you, it's very different. But the difference is to do with what's going on at the surface. Basically, a dead leaf, nothing is happening. The energy is just coming in and it's heating up that leaf, or whether it be some material, whatever. But if it's not got the right capacity already in it to do something with that energy, it's not going to do anything. It's just simply going to dissipate the energy in that leaf. So we need to realize that when it comes to what we're talking about really is photosynthesis, that those of you who know the details here will know that it's the chlorophyll on the leaf which acts as a catalyst to an important biochemical reaction, such that the water which is in the plant and the carbon dioxide in the air, with the radiant energy coming in from the sun, will only do something because of that water and the carbon dioxide, but importantly, because of the chlorophyll, which of course is highlighted there. That is a catalyst, but it's a very important catalyst. Without the chlorophyll, there won't be the machinery. I'm using that term and I'm going to define it more carefully in a moment, but I'm going to use the term machinery. I don't mean nuts and bolts. In this case, it's a biochemistry machinery, a surface chemistry. So the conclusion is that energy on its own does not lead, and I will define this term a bit better in a moment, it does not lead to the raising of what we call the free energy. I'll define it properly in a moment, but I want you to just get some sort of intuitive idea as to what I'm thinking about here. The energy available to do something useful. I'm going to define it more accurately in a moment, but we call that the free energy. The energy available to do something good or something useful. Maybe not always good, particularly if you're doing something nasty to somebody, but that's another issue. But the energy available to do work. So now we come to what I maintain is a thermodynamic principle of a non-isolated system. So I'm actually addressing head-on the objection of those who are rank atheists who are trying to say, and they've written about this in papers galore in the literature. I'm not going to quote them all, but I've read the literature and they will argue tooth and nail that basically with a compensationary view that you can have the entropy going down in one area at the expense of the energy going up in another area. And it's an argument entirely from a naturalistic point of view. But I'm arguing here that in a non-isolated system, so an open system, you might say, the free energy potential will never be greater than the total of that which was already initially in the isolated system. And maybe that coming in through the boundary, maybe somebody's going to throw in some sort of device which will be of help to you. Suddenly, an alien puts something in to that system which wasn't there before, or something comes through the boundary. But other than that, you're never going to actually gain free energy unless you've got something there already which enables you to do it. In other words, the chlorophyll of the leaf is what is absolutely essential, and the whole biochemical system. We call this free energy H, which is an energy term. It's really the overall energy available, which includes everything, minus the entropy term. So it's really the energy available to do work. Loosely, the free energy you might regard as the organized energy of the system. So, is that then true? I ask the question again, and the answer is thermodynamically it's not true. Random energy does not on its own build machines. You could have a multiverse of energy flow, but if it's essentially random energy, and if there is no ability to capture the energy to make it go down specific electrical pathways, chemical pathways, whatever pathway you want to consider, and I've written G because I'm thinking in terms of gas dynamics where it's the Gibbs free energy, but you'll find that in electrical engineering it's the Helmholtz free energy. Let's worry about that detail. I just want to give you the essence of this argument, that you've got to have some system which actually brings that energy to be of use. And that's what my friend Richard Dawkins did not grasp. And he's no thermodynamicist. Now, I maintain then that there is a thermodynamic principle of non-isolated systems. You'll never see this written in the books because the implications are too heavy for them. That's my reason anyway, that I can think is what's going on. Nobody's ever formally put this in books. I put it formally in my papers, and it's up to others if they see that actually this needs to be regarded as a principle. It's almost a law. The free energy potential is never greater than the total of that which was there already, plus that coming in through the boundary. So now I'm going to go a bit deeper. You say, well, that was deep enough. Well, okay, this may be you, but please don't worry. We will come in maybe with some rescue devices as I go on. And I've got various illustrations to try and help you. And if you want a copy of these notes afterwards, you're welcome to them. I said I would come to some definitions. I'm going to define what I mean in this talk only as the term machine. I'm going to give it a tighter definition. Now, I've chosen to use that word. Maybe some would argue you could use another word, but I've used that word, okay? So you'll just have to put up with it if you don't like the word. I'm going to say that all natural molecule formations are like this illustration of Slinky. I don't know whether you've seen these, played with them, but they basically are, they look as though they've got energy of their own, but they're not actually. They're just simply going to equilibrium. Somebody has to set the spring, and then it will bounce around as it comes to equilibrium. And of course, sometimes, as it comes to equilibrium, it does some very interesting things, like walking down stairs and stuff like that. You all look aghast. Have you never used a Slinky? Come on now, Alex, you look so serious, but I'm sure you have used one with your... He just about admits it.
The problem about these things is they are easily get destroyed when you...
Yeah, they certainly do. So they're all made of plastic now, and I prefer the old ones, the metal ones. But I've still got my original one at home, and I think there's a collector's item in it. But anyway, so the spring then is set, and so if you like, a little input of energy is given, which enables it to do what you want to do just for a little while as it settles down. But there must be, molecules basically have to be set or injected with energy down a very specialized biochemical pathway, as you'll see in a moment as I bring you on to ATP, which I will discuss. You have to have a very specific pathway to bring energy to make them do what they do. We'll deal with that detail in a moment. This is just the principle. So I'm saying that a machine is a device which has locally raised the free energy, or we might call it ordered energy. So just carrying on with this idea, just to give you some illustrations. Chairs are very useful, but it's not an energy device. I just say it is a device. But in my definition, it's not a machine. Without it, of course, you wouldn't be relaxed, but at least, you know, they have very useful function. An ejector seat, which is also a chair, is a very special type of chair, which, as you well know, is primed with energy, ready to be released in a moment when the F-16 or whatever it is in danger of crashing. And so the ejector seat is a machine. The other one, I'm going to say, is a device. Another illustration for you, tornadoes. You might say, well, that's using a lot of energy. Yes, but I would suggest to you that, as I've put here, it's not something which is repeatable with predicted regularity or measurable regularity. That is, yes, you know that there's going to be, the weather forecaster may say that there's going to be some sort of tornado, but you wouldn't say, okay, I will place my cup specifically at this point to stir my cup of tea by the tornado tomorrow. You won't be able to do it because it's not obviously something which is acting with specific purpose down a particular energy pathway with an intent. And you might say, I'm begging the question, we can discuss that afterwards. That, of course, the naturalist will fight tooth and nail. Whereas a wind turbine is evidently a machine because it converts energy with regularity, and of course it's used to produce, in this case, electricity into the main power lines. So let me now come on to an illustration which I find very helpful because it links with what I was saying about the photosynthesis in the leaf. This is not a wind turbine, it might look like one. It's actually a solar cell. And what I've got here is, you'll see here, it's actually working. There's a solar cell which is causing this to go round. If I put my hand over the solar cell, that will just completely stop, which is basically like a dead leaf. So a dead leaf, I can feel the heat of this lamp coming onto my hand, but the heat's doing nothing, it's just heating my hand. Whereas as soon as I put a solar cell there, actually the temperature there will be slightly lower. And indeed, you can tell when you've got real plants in the room or artificial plants by just putting your finger on the leaf, and you'll notice that it's slightly cooler than room temperature. Why? Because some energy is coming into that leaf, doing the photosynthesis marvel, which it really is, and it clearly is an illustration that we have there a creation by an intelligence. So you can see where I'm going with this talk. Look at other things like feathers. They are marvelous, and by the way, they also, for different reasons, show design, but not along the line of argument that I'm speaking about now. But as I mentioned earlier, and I'm putting a little bit more rigor to it now, photosynthesis, which is like this solar cell, except that it's a natural occurring solar cell. You might say it's not producing electricity, but it is producing the most important sugars that the plant loves. And we all love, well, most of us love sugars, and the plant needs sugar, and of course at the same time it gives off carbon dioxide. So let's now look at some details in the cell. And the thing that I want to look at in particular, there's so much we could look at in the cell. I'm not an expert and I don't claim to be a biochemist here, but I've had to read and look at what others have written. And so I pick up the engineering implications of that which I read. One of them is an amazing machine called the ATP synthase motor. This is actually an electrostatic motor. It's not quite what you'd call a traditional electric motor, but it's an electrostatic motor driven by hydrogen ions going across a membrane. And as the adenosine diphosphate comes in, it adds an inorganic phosphate pi. That's not 3.141 there, it's an inorganic phosphate, and it becomes not a diphosphate, but a triphosphate. It becomes an unstable molecule. But it's hugely important because this unstable ATP, adenosine triphosphate, now wants to use its extra energy. And it's used in a number of ways in the cell. Notably, we'll see in a moment the polymerizing of DNA, but there is another function as well which I will mention. The other one I will mention first is, I think we've just got time to play a bit of this, the kinesin walking molecule. So I'll just play a bit of this video.
Meet the kinesin. Masterpieces of microengineering, kinesins are miniature motorized machines that carry cargo from one part of the cell to another, walking along self-assembling highways called microtubules. Known as the workhorses of the cell, kinesins have 2 feet, or globular heads, that literally walk 1 foot over another along the microtubule, pulling their cargo to its destination. Each foot possesses 2 special locations called binding sites that interact with other molecules. One site attaches to the microtubule and the other binds with ATP, the energy molecule of the cell. When one foot binds with ATP and uses its energy, the foot flips over, resulting in the walking motion.
But that just shows you one example of how ATP is used. It's used in a myriad of ways, right? Down special chemical pathways once it's been made. But one of the other usages is for actually adding and polymerizing to the vertical parts of DNA, which are sugar phosphate bonds. You've got the nucleotides going across, which we know, and this is aside to my arguments at the moment, but you know that the nucleotides, of course, code as triplets for the amino acids. But what's amazing is that there actually is a polymerizing function which uses ATP. Let me explain this a little bit to you. You see, when Professor Richard Dawkins thought that he'd nailed it by saying there is loads of energy out there, he was trying to argue that abiogenesis and indeed developments after abiogenesis, even if you could get that working, which I maintain that thermodynamically it just is impossible, he was saying that there is much that could be done just simply by adding energy. But actually, the energy has to come in a very, very special way in order to add vertical parts to the construction of DNA. Let me just illustrate by just using this schematic. You've got the nucleotides, which are the blue bases there, and then the sugars, sugar phosphate bonds are the green and the yellow. So you've got the non-coding other side of the DNA. And what I'm maintaining here is that unless you've got the ATP, the details of which I'm not going to go into now, but unless you've got the ATP, there is not the energy in order to make another sugar phosphate bond be added to what was there already. So there'll be a sugar phosphate bond attached to that adenine, okay? And in order to perhaps add, say, another thymine, that is a thymine nucleotide, you need a sugar phosphate attached to that thymine to add underneath. Well, you wouldn't be able to do it because the energy pathway is not there. It's actually trying to do something which it can't unless it becomes a triphosphate thymine. And then it bolts on and it's got its nucleotide ready or its base ready to then be to do what it's going to do with a non-coding part on the other side acting similarly. So I'm interested in the energetics of this. So the point I'm seeking to make here is that you have a free energy issue even with the polymerizing of DNA. You're trying to go upwards. You're trying to go in an endothermic direction where there is nothing in the system which will let it do it because the free energy is not there to climb that hill. it's always going to go downhill, just like we primed the slinky earlier. Everything will go downhill, literally. It is downhill as it goes down the steps. So that's an illustration or an analogy of what's happening here. So if I want to go to an energized intermediate, which I've said is absolutely necessary in order to add another sugar phosphate into the vertical part of the DNA, then I need an energized intermediate, which is where the ATP comes in, which then, once it's been brought in, then relaxes down to the finish line, which is still above what it was before, but it now enables this to happen. We call that basically an activation energy. I've worked a lot in the energetics of other systems using what we call activation energy, so this is very much in the area of the thermodynamicist. So how do we make DNA thermodynamically? Well, you have the raw building blocks, and you want to climb uphill to produce DNA, but you can't do it. The free energy change is positive, and you can't do it. Naturally, the energy will not be raised. It will always go downhill. So you have to actually go, as I've said, to some other compound which is specifically put there by a whole system of biochemistry reactions, which actually, I'm going to show you in a moment, produces ATP just at the right moment, such that the ATP can then be used as a high energy compound to raise those raw building blocks of a diphosphate into the triphosphate that it needs to be, which then bolts on to the existing DNA strand. So once you've got the energized intermediate, then the free energy change is negative and it relaxes into this extra bit of polymerized DNA strand, the vertical part of the DNA. So in summary, ATP is a very unstable substance. It's never found outside living cells. It needs highly organized chemical pathways for it to be made, and yet DNA cannot be formed without it. So the energy conclusions from this work are that nucleotide monophosphates are needed to produce DNA. There's very high activation energy. It's very endothermic. No reaction, it can't happen. But if you produce nucleotide triphosphates, then you've got a low activation energy. You do have an activation energy, but it's exothermic, it's spontaneous, it's irreversible. It does happen through the intermediate ATP. So where does the ATP itself come from? Because we need it, obviously. Well, amazingly, ATP itself does not form spontaneously. It is formed by another very endothermic reaction, which I'm not going to have time to put. All I would need to do is to actually put up the chemistry, and most of us would get fazed by the huge, long list of chemical reactions involved in the making of ATP. But it is unstable. It is produced itself by cellular respiration involving existing ATP. So it's a chicken and egg situation in the production of ATP. So it needs organized structures in the cell to produce it, and a source of energy and very specialized enzymes, that is basically catalysts, involved in the reaction. So this ATP is manufactured by enzyme catalyzed reactions in a highly regulated chemical environment. Most of us, if you've got any knowledge of engineering, and most biologists, if they've ever really thought about the engineering implications, must see immediately that the chemistry, the physics, the thermodynamics is shouting that this is a system which cannot be got by some sort of appeal to, oh, there's loads of energy out there, as Richard Dawkins famously said to me. Well, if you thought that was bad enough, I've got something more to say. And it's the connection with information. You say my head hurts. Well, I hope you've understood thus far the logic of what I'm saying. Now we're going to deal with information. I've got 2 papers out on the table there, but they're on your app as well. I specifically asked them to be added. The first one goes as far as basically where we're at now with a little paragraph about information. The second one develops this further, and I end up with principles of information exchange. Now, I just want to quote at this point a person who admits that actually we're onto a loser here to argue, and he's not a Christian, he's died now, but that you cannot argue for information arising out of matter. Information, George Williams said some years ago, doesn't have mass or charge or length in millimeters. Likewise, matter doesn't have bytes. You can't measure so much gold in so many bytes. It doesn't have redundancy or fidelity or any of the other descriptors we apply to information. This dearth of shared descriptors makes matter and information 2 separate domains of existence, which have to be discussed separately in their own terms. Now, I almost agree with him, but not quite. Not quite. He's essentially correct, except that there has to be an overlapping region where information interacts with what technically you should call a substrate of some kind, matter basically. Just like the information in this Apple computer, and by the way, Windows machines also do the same, but little, you have to kick them to make them work, but you know what I mean. But there is an interchange between information and matter. Now, let me just develop this point. We have to be a bit cautious, but there are a number of people who've written on this, and of course the intelligent design community has a wealth of people who've thought into these issues. It's been said quite rightly that information requires specific sequencing. It cannot just be a random set of letters. It's got to be letters in a particular sequence which can be understood. And mutations generally will not produce specific sequences that you're intending. You can get a fluke where, you know, a lava lamp might produce the number 22, and you think, well, that's just a fluke. But if that actually began to say 32, 42, 52, you'd then say, well, there's something really out there trying to tell me something, okay? So this is an intuitive argument, okay? Also, information, and this is what leads me into something which I owe an awful lot to Werner Gitt here, the German thinker who's a brilliant person. I've often had interactions with him. And Werner Gitt rightly talked about levels of information. He actually talks about 5. I'm just going to mention 2. Information involves codes and language, and it involves a level where whatever code or language is being used, there is a message. So there is a sender and a receiver. It involves communication and purpose. If you're going to use the analogy of a computer, hardware doesn't write software. I know we have expert systems. We talked about artificial intelligence. And of course, we know that things are hugely advanced beyond what the basic machines that we use every day are doing. We know that there is a sense of, quotes, design, unquote, going on with artificial intelligence. But someone, somewhere, has actually written the system which actually begins that operation. We may end up fighting the machine, as famously the film 2001 shows years ago, made in 50 years ago. I saw it last week and I thought, what a most boring film it is, based on the book by Arthur C. Clarke. But I don't know whether you've seen it, but you just sit there waiting for something to happen as all the music goes on. I don't know how on earth that film made it. But anyway, it ends up with everybody dying because the fellow who's the hero of the plot ends up fighting the machine, you know, and the machine says, you're trying to kill me, you know. It's very interesting. It has big import into the AI discussion we had earlier. But essentially, that machine was designed by someone, even that machine. So music, to use another analogy, Lydia will like this, she's a musician, but the musical score is not the same as the music. So there's all sorts of analogies you can use here. So let's just try and examine then, just in these last 10 minutes, this issue of information in a little bit more deeply. We can use the analogies, and they can go so far with them, and we all appreciate them. And we are in the area that George Williams rightly said, well, we're struggling for definitions here. We could use the term bit, which has been very useful for, and I'm not going to put up a slide on this, for the transmission of information. We can build up theorems that Shannon designed or spoke about and wrote down very carefully for the transmission of information. But actually, they don't help us for the origin of new information. Shannon's theorems are all to do with really transmission of existing information. Now, we know that transmission today is essentially done in binary systems. Somebody has once said there are these types of kinds of people: those who read binary and those who don't. If you don't get that joke, just think about it. Right? So if you read it binary, you know it's saying 2. But if you're not, you see it as 10. So we put information into ones and zeros. And so it is absolutely true, what was said earlier, we knew it intuitively, that information requires specific sequencing. But of course, it must be built on an agreed code between the sender and the receiver. That's essentially Werner Gitt's points, which I'm hugely grateful for his work. He's written the book, In the Beginning Was Information, which is quite old now, but it's full of very good information. So we can make a significant point here that language and code is not defined by the material itself. And that's where George Williams was trying to pull the naturalistic community to recognize this. I once went to a discussion group in Michigan at a famous laboratory where they were discussing protein folding. And I thought, well, I'll go along and listen to it because I am interested in this area. I'd actually spoken on the Bombardier beetle work, that is another subject that is part of my research. But I thought I'd just go along and just listen to this discussion. And I dared to make a comment at one point. And I spoke about they were discussing why proteins fold in a particular way. It's another big problem in biochemistry. Nobody's yet resolved why proteins fold in a particular way, which they must do in order to build literally the geometries which are needed, which I haven't gone into in this talk. And nobody's been able to work it out properly. They've all tried to appeal to a naturalistic system to actually work out how on earth these proteins end up folding the right way. So little me puts my hand up and says, well, could there be that there is an information system in here which we haven't yet discovered? You could have heard a pin drop. As they all stared at me and thought, as though I've sort of broken the rules of the game. But I'm convinced, by the way, that matter of protein folding will only be resolved when somebody finds that it may be to do with the DNA, I'm sure it is, it's to do with some information system filtering down to actually say to those proteins how to fold. So the language code, because they were trying to say that the system is somehow all understood by the energies in the proteins. No, it's not. It must be to do with some information. So that's why I've made that illustration. What's that saying? Well, that is actually Morse code for the words, I'm trying to tell you something. So the language and the code is not defined by the material. It's a very important point. And George Williams, wasn't a believer as far as I know, agrees with that point. But there's also a second point, which is again from Werner Gitt, which says that message transcends the language and the code. So as I've got another Morse code here, and this, of course, is illustrating that you need to understand the code. Once you have understood it, you can write it in two ways. It's actually the message, John loves Mary. Now, Mary, I'm sure, would appreciate it if it wasn't written in Morse code and wasn't even written on the sand. She'd probably appreciate a hug. So there are two issues here, which I've just summarized again in this slide. I'm just repeating, so you've got the point. That message transcends the language and the code. The other illustration, of course, is the Rosetta Stone, where the message was written in two main languages. There was a third, and that suddenly meant that you could understand the Egyptian hieroglyphics. And the first point that I made earlier, which is that language transcends material. Now, we need to now come to these principles of information that I'm now beginning to realize are also needed. Stephen Jay Gould, I had the privilege of hearing him speak at Leeds once, but he spoke of non-overlapping magisteria. Now, George Williams was really heading in that direction when he made his comment, that somehow that there is a physical world with the natural sciences and a non-material reality. To be fair, Stephen Jay Gould was more thinking of possible spiritual reality, but it even applies to this issue of coding and software, which George Williams was referring to. And I'm going to say that that's not a correct assumption. We actually need to be considering it in this way, that you've got the physical world, the non-material reality, which does include other areas like mind and consciousness, but I'm actually just thinking about information, software, and intelligence. And I'm saying it lies in that area. Remember the quote that we had of George Williams? I'll put it up again. There are two separate domains of existence, he says, which have to be discussed separately in their own terms. Both right and, in my view, slightly wrong, because he doesn't seem to be admitting that there is an issue here of a connection between the thermodynamics and the information. Let me summarize that this is basically what I'm saying, that the evolutionary view says that matter and energy is all that there is. Abiogenesis took place. We don't know how it happened, but it's the only game in town. It formed the nucleotide system. It became the information system, which then gives mind and intelligence, which we've been discussing in these in the AI discussions here. I'm saying, as we all know, that as believers, that mind and intelligence created information. In the beginning was the Logos, John 1:1. That this means that the Lord himself designed the nucleotide system, which is in the DNA. And this is the bit which George Williams, I think, is missing. There is a thermodynamic effect of information. The problem is that you cannot simply say that if you've got this effect, you've necessarily got information, because you could also have noise, which will have a thermodynamic effect. So you cannot actually overcome completely this issue of trying to connect with a one-to-one relationship, information with a thermodynamic effect. I've thought long and hard about this, and I don't think you can, because you could have a wrong message in a computer which actually has a thermodynamic effect. And you wouldn't be able to distinguish between the thermodynamics of a wrong message and the thermodynamics of a correct message. So although it would be delightful to say that you've got good thermodynamics, or you've got some thermodynamics which is this number when you've got the right message, I don't think you can go there. So to a certain extent, George Williams was right. But I am going to say that there are principles, and I owe a lot to John Sanford on this one. John Sanford wrote the book Genetic Entropy and the Mystery of the Genome. It's well worth reading. And when I talked with him privately, he said, Andy, actually what really you have here are principles of information. So we had a long discussion. So I actually owe a huge amount to John Sanford for pushing me on this. And so I eventually did agree to putting principles of information exchange in the second paper. And they mirror the laws of thermodynamics. This is the interesting point. The first principle, you could call it a law, but I think that's being a bit arrogant to say that. It's up to others to say whether they think this might be a law. The first principle concerning information, language, and communication. Apart from creative intelligence, information cannot be derived from nothing. There has to be a precursor bank of such information. This is a parallel principle to the principle of conservation of mass and energy, the first law of thermodynamics. So I'm now really constructing a worldview to look at information from an intelligent design stroke creation perspective. The second principle is this one. Apart from a sustaining intelligence, all information degenerates in terms of its functional utility. Information will corrupt unless it is sustained by an intelligent agent. So books eventually deteriorate. You put a book out in the sunlight, or you have water damage, or whatever it is, just gradually decays. That's just books. You well know that computers, even an Apple one, eventually has to go into the bin, you know. And if the electricity goes off, you may be able to sustain it for a while with battery, but then you've lost it. This principle is a parallel, of course, to the second law. And indeed, there is really a connection because all information is on a substrate of some kind. And the substrate itself is suffering from thermodynamic decay, the second law, or the principle of thermodynamic decay. So this principle is a parallel to the second law of thermodynamics, or even the non-isolated version that I gave. And then there is a third law, the principle of information gain. The information content in a system is never greater than the total of that which was there already, and that coming in through the boundary of the system, which of course is an exact mirror of the law that I maintain is a law for non-isolated thermodynamic systems. Remember I mentioned that there was a version of the second law which actually becomes a law for non-isolated systems. Well, it's exact parallel to that. So this third principle is really just that principle again, but expressed in terms of information. So I conclude, ladies and gentlemen, by saying these following conclusions. Naturalistic origin of molecular machines is essentially against thermodynamics of open systems. Thermodynamics drives naturally to equilibrium. It doesn't go uphill. Nowhere ever has this happened naturally. If somebody can quote an example, then you'll get the Nobel Prize. Nobody's ever done it. Open systems cannot of themselves build free energy. Sorry, that's this second one there. Now let me just mention two other things concerning, or another slide concerning the conclusions on information. Information is non-material. It sits on matter and energy and uses it, but it's not defined by it. It connects with matter and functions even at molecular level, at molecular levels, perhaps I should have said. I've got a mutation there. There are principles of information exchange which parallel the laws of thermodynamics. And as I've just added since I've been here, I so much valued the discussion we had the other day. I thought it was wonderful. This feeds into the discussion of consciousness and mind-body. It obviously is only at the periphery of that discussion, but nevertheless it feeds into it. It also connects to the discussion on AI. And of course there are spiritual implications here. You well know that Paul amazingly said on Mars Hill, "In him we live and move and have our being. I think that verse is extraordinary because it's basically saying that even those who hate the very God who made them only live because God sustains them, gives them the breath they breathe, gives them the DNA that they need, gives them all the ATP working as it does, right? To use all the energy and the food that God provides for them. My German friends here will love me quoting Kepler, and I do hugely respect Kepler and many other great scientists, but he famously said, thinking God's thoughts after him. And I think that's what humbly we should be doing. Hebrews 1, as you well know, says, who being the brightness of his glory and the express image of his person, and upholding all things by the word, it's not the word logos in that place, but nevertheless it's the same basic point that Christ upholds all things. And if he didn't uphold even the nails in his hands and his feet, if he didn't uphold the breath of his persecutors, he was the one who had to do everything to even sustain the universe while he was on the cross. The mind boggles. Christ is the sustainer of all things. Even as he bled and died for us, he still was doing that. So I end, in the beginning was the Word. As Git famously said, it wasn't Git, it was, what's that American gentleman who was the head of for a long time he was friend of Stephen Meyer, leading the intelligent design movement. He said it wasn't in the beginning were the particles, it's in the beginning was the Word. I'm trying to remember his name. He wrote the book Darwin on Trial. Philip Johnson, yeah. It's not in the beginning were the particles, it's in the beginning was the Word.